Why NASA hid the Threeey Atlas anomaly. Fire in the sky. The numbers jumped when they shouldn't have. A sudden sunward push lit up the acceleration plot, alarms chimed, and someone whispered, "That's not a comet." We recalculated. Again. The curve refused gravity's leash. No tail, no gas, just motion that didn't care what the textbooks said. Atlas had flagged a new interstellar visitor, our third. The light was wrong, the force was wrong, and the clock was already running out. If natural forces can't pay the bill, you ask the question no one wants to say. To see why, we rewind to the first night. Detection: the night Atlas blinked. It began as a routine sweep. The asteroid terrestrial impact last alert system, Atlas, was breathing through the sky, frame after frame, hunting for motion that didn't belong to the starfield. On a screen in Hawaii, a faint streak hopped between two exposures with just enough swagger to be interesting. The software tagged it, calculated a provisional track, and handed the residuals to a human. That's when the eyebrows went up. The motion didn't sit cleanly on an ellipse. Early astrometry, the tiny measured positions of the object against background stars, left small, annoying residuals. That happens especially with faint targets. But as additional frames rolled in, the fit moved from messy to odd. Atlas spun up a preliminary orbit solution, and the number that matters in that moment is V infinity. The speed the object would carry far from the sun's reach. It wasn't zero. It wasn't close. Hyperbolic. 3 letters followed, I for Interstellar. The catalog would later call it Threeey Atlas. Internally, the mood flipped from routine to urgent. We missed our chance to stare at Oumuamua for long. We caught Borisov, but it looked like a textbook comet. This one might be the tiebreaker. Phones came out. Slack channels pinged. Request pan-SDARRS cross-match. Ping ZTF. Pull Gaia Doctor 3 stars for local frame. Tighten the plate solution. Within an hour, emails fanned across time zones. If you had a telescope and a clear night, you were drafted. Meanwhile, a small drama played out on a mountain under clouds. One team had booked time, perfect for early Spectra, only to watch whether radar turned green. Another, down the road, saw a gap open in the clouds long enough to grab a few noisy images. Those exposures, stacked and nudged, showed the object brighter than expected in one sequence, dimmer in the next. Someone plotted a light curve on a laptop in a cramped control room. The swings were wild. High-amplitude shifts that, if real, could mean an extreme shape or a rapid tumble, or both. Atlas pushed out a minor planet center telegram. Observatories adjusted their cues. A mid-sized scope in South Africa picked it up, then a 4-meter in Chile. In the rush, everyone felt the same pressure. Don't repeat 2017. Back then, the window closed while arguments opened. Not this time. Get Spectra now, one Pi wrote. Even low SN, anything. Telescope operators triaged. Do you burn precious minutes on a faint object that might vanish behind twilight? Or keep the schedule and risk losing your shot at the first chemical fingerprints? Across the network, early photometry started to land. The brightness curve refused to settle into a simple spin period. Solutions diverged. You could make a rod work. You could make a disk work. Both felt like lies told by limited data. Stacked images searched for fuzz, any hint of a coma, the gaseous halo that should bloom as sunlight heats volatile ices. Nothing obvious. Not at that distance, not at that time. An astronomer in Spain pulled a night shift, eyes sandpapered, flipping between astrometric reductions and coffee. He tightened the reference stars using Gaia to shave down systematics. The orbit fit improved, but the whispers began. If the path isn't purely gravitational, we'll see it in the residuals. Another team ran Monte Carlo simulations, thousands of possible orbits with slightly different starting conditions, to test how sensitive the track was to the early measurements. The spread was tight enough to be confident. Interstellar, inbound, and on a course that would bring it close to the sun in weeks, not months. Here's where the adrenaline kicks in. Survey telescopes find things. Follow-ups explain them. But the gap between detection and understanding is a sprint through gatekeepers, schedules, weather, calibration. A tiny discrepancy in a flat field, a misbehaving guide star, a thin film of dew, all of it can turn truth into noise. Still, the data hose opened. At the University of Hawaii, someone pulled up Oumuamua papers and highlighted the battle lines. Radiation pressure advocates versus outgassing modelers. Hydrogen ice, nitrogen ice, carbon monoxide, each came with an elegant story and a nasty problem. Hydrogen wouldn't survive the journey. Nitrogen would leave traces. Co should have lit up lines we can see. Borisov, in contrast, had a coma that behaved as expected. No mystery acceleration. No fights over sail-like shapes. If Threeey Atlas landed between them, no coma but a measurable push, the arguments would come roaring back. A call went out for spectrographs sensitive in the near-infrared. If there was CO or CO2, we had a shot. A Northern Hemisphere team, battling mediocre seeing, squeezed out a spectrum with little confidence. Hints maybe of CN. But the calibration lamps had an issue, and everyone knew better than to hang a theory on a ghost line. While that was happening, a microstory unfolded in a suburban kitchen. A postdoc spooned cereal while her phone lit up with group texts. She canceled her morning class, drove to the observatory, and spent the afternoon writing pipeline code to catch sudden brightness spikes. She set a trigger. If the amplitude exceeded a threshold within an hour, her script would fire an alert to retask a smaller robotic scope for dense sampling. At 2:13 a.m. it pinged. The swings were real. By the third night, the object had a personality. It flashed and faded like it couldn't make up its mind. The orbit pinned down the interstellar status beyond doubt. The name Threeey Atlas started appearing in subject lines, and a quiet, uncomfortable realization crept in. If this thing was being pushed by something other than gravity, we'd have to fit the trajectory with a force term. A small one, sunward and stubborn. You can't explain what you don't see. First looks come in messy. The team agreed on one thing: get closer to perihelion, watch the heating kick in, and see if a coma blooms. If outgassing drives the push, the gas will betray itself. If it doesn't, the mystery gets teeth. First looks, shape-shifting light. By sunrise after night 3, the brightness curve looked like a heart monitor, peaks, lulls, and another surge arriving early, like the object was arguing with our period fits. A simple spinner would hum a rhythm. Instead, every new photometry chunk slid the period around. Force a 3 to 7 hour rotation and it held for a night, then broke the next. That instability set off the shape debate. An elongated rod would throw big brightness swings as it rotates, like a baton flashing its broadside, then its narrow end. But the amplitudes we saw pushed into the territory where a rod becomes almost absurdly long for its thickness. So people flipped the mental model. What if it's a disk? Ultra-flat, like a pancake, flashing bright when it presents its face, dropping when it turns edge-on. That could deliver wild amplitude, too. The trouble is, both shapes strain what we expect from icy rubble that's been drifting between stars for millions of years. Nature can stretch, but how far? Stacked images from multiple sites tried to settle another question. Where's the fuzz? As the object approached perihelion, even weak volatiles should start boiling off, seeding a faint coma. Teams stacked exposures, aligned on the moving target, and hunted for the halo. Thresholds were so low that a whisper of dust should have shown. It stayed clean, no tail, no steady coma. If dust was there, it hid below our limits or came off in bursts too short to smear the stacks. Thermal versus optical estimates complicated everything. In optical light, the object's brightness translated to a size that depended on reflectivity. If it was bright, high albedo, it could be small. If it was dark, coated in organics or weathered crust, it had to be bigger to throw the same photons at us. But the swings in brightness suggested dramatic cross-section changes, implying either a truly extreme geometry or a surface with patches that reflected like mirrors in some orientations and like charcoal in others. Without a reliable thermal detection to anchor size and albedo, every model carried a slippery caveat. We chased composition early, knowing it might be our only honest lever on non-gravitational forces. A couple of provisional spectra hinted at volatiles, but the signal to noise was a bully. One reduction showed a wobble near a CN band. Another, pushed hard in the near IR, teased a bump where CO could live. Then the caveats rolled in: sky subtraction artifacts, calibration lamp drift, thin cirrus. Everyone had the same rule. A hint is not a line, and a line is not a detection until it survives an enemy's pipeline. Why did the geometry and composition matter so much? Because the force depends on them. If outgassing is pushing, then where the jets come from and how the object spins will decide the direction and timing of the shove. If radiation pressure is in play, the area-to-mass ratio is king. Misread the shape or the surface, and you'll fit the wrong force to the right orbit. We'd already learned that lesson with Oumuamua. Every elegant fix fell apart on one stubborn detail. Hydrogen ice couldn't make the trip. Nitrogen ice should have announced itself. Carbon monoxide should have lit up unmistakable lines. Borisov stayed honest. Classic comet, classic coma, no mysterious push. Our third visitor was threading the needle. Measurable acceleration, but no reliable coma. Meanwhile, one subtle detail began to nag at people who stared at the light curves too long. The peaks weren't just high, they were asymmetric. The rise to maximum arrived faster than the fall, then flipped on a different night. That's the kind of quirk you see when tumbling complicates a simple rotation, or when the reflective properties change with angle, specular patches glinting only when everything lines up just so. A micro story played out on Slack. Check the phase angle dependence. Already did slopes weird. Weird how? Steeper than typical low albedo comets, flatter than bright asteroids, it moves. Phase angle matters because sunlight and viewing geometry can fake or amplify brightness swings. At certain angles, rough surfaces backscatter light more efficiently. At others, they go dull. If Threeey Atlas carried a surface with mixed textures, glassy patches, matte crust, maybe frost clinging in pockets, then the same rotation could produce different light curves on different nights as the Earth object sun angles slid. That meant every period solution baked in assumptions that might not hold 2 days later. A late night call turned one hunch into a working hypothesis. What if our size estimates were wrong because the object wasn't a single body? Not a cluster, not a debris cloud, but a shape with deep concavities, snowflake-like, or a shard with voids, that changed its effective cross-section dramatically as it turned. In one orientation, it's all face. In another, it's a skeletal profile. The team ran synthetic light curves through a simulator, feeding in absurd shapes to see if any could reproduce the amplitude and chaos without invoking impossible spins. A few did. None were pretty. Then came the most honest line anyone wrote that week. We might be looking at a geometry that flips our brightness assumptions. High reflectivity patches make a small object look big. Porosity or fractal structure spikes cross-section per mass. Both push us toward forces that need lots of area per kilogram. Both kept colliding with the same missing piece, a coma we could point at and say there. As the object slid sunward, every telescope cue felt the same strain. Keep staring because the moment a coma appears, the story shifts. If it never does, the light curve becomes our only honest witness. We were learning the outlines of a personality, capricious brightness, unstable period fits, no clear fuzz. The shape wasn't just odd, it was a constraint. And that constraint would force us soon to write a new term into the equations. Ghosts of one eye and two eye. To understand why the room got so tense, you have to hear the echoes of 2017. Oumuamua arrived like a riddle, small, dim, and moving wrong in just the right way to keep people up at night. Its brightness swung wildly, so we argued shapes. Was it a cigar, long and thin, flashing as it rolled? Or a pancake, thin and broad, glinting when it faced us? The cigar fit early period guesses. The pancake fit later amplitude constraints. Both fought the same wall. The non-gravitational acceleration that nudged it sunward without the coma, a normal comet would wear like a badge. First fix on the table was outgassing. If jets of vapor hissed from its surface, they'd act like thrusters, except the usual suspects wouldn't cooperate. Hydrogen ice sounded clever, sublimation without visible lines, but it wouldn't survive interstellar radiation for millions of years. Nitrogen ice got traction next. Release N2 and you get clean thrust with faint signatures. But models said you'd erode too quickly, and any nitrogen-rich crust would likely be detectable in some fashion. Carbon monoxide seemed plausible because CO can lift off at low temperatures, but multiple teams hunted for CO lines and found nothing convincing. Each model looked elegant until it hit the data. Then came the radiation pressure idea. If sunlight's momentum pushed on a very low-mass, high-area object, think sheet, not boulder, you could match the observed acceleration. That required an area-to-mass ratio far beyond typical rocks or ice. Cue the Lightsail whispers, not as a claim but as a boundary condition. To get that push, you're in sail country. Most astronomers weren't ready to plant a flag there, but they couldn't ignore a math problem that pointed that way. 2 years later, Borisov gave everyone breathing room. 2IG Borisov looked like a comet should, diffuse coma, dust, gas, spectral lines where they belonged. Its path tracked gravity with the small, predictable tweaks you see in standard comets. It was the baseline, the control, the reminder that interstellar objects could be boring in the best possible way. If 1I was the outlier, maybe we'd overfit a mystery to noise. But 3I Atlas refused to behave like Borisov. The Coma stayed below detection limits while the trajectory hinted at a steady sunward push. The community split reappeared like a scar that never healed. On one side, exotic but natural. Maybe we're seeing a new debris class, porous aggregates, odd ices, crusted surfaces masking tiny jets. On the other, artifact talk. Not declarations, caution stuck, but a willingness to say, if radiation pressure fits, we should at least test the sail hypothesis against the numbers. Here, S where the parallels sharpened. Like Oumuamua, 3I showed large brightness swings that made normal shapes uncomfortable. Like Oumuamua, it hinted at non-gravitational acceleration aligned roughly sunward. Unlike Oumuamua, we were watching in near real time with lessons learned and pipelines tuned for anomalies. We knew what to ask. Is the acceleration magnitude consistent with sublimation at the observed distances? Do the upper limits on dust production kill the jet story? Does the phase angle dependence of the light curve suggest specular reflections you'd expect from flat facets? Meanwhile, the differences mattered. Oumuamua arrived with almost no warning and slipped away before we could pound on it with instruments. 3I had a slightly longer runway, enough to set tighter caps on gas and dust. Borisov's Coma told us not every interstellar traveler is weird. The trio formed a triangle of constraints. 1I with the push and no fuzz, 2I with the fuzz and no push, 3I threatening to rhyme with 1I in real time. What nobody knew at the time was how merciless the math would be once we fit 3I's trajectory with a forced term. The direction looked sunward. The magnitude pressed past comfortable sublimation models unless you stretched composition, geometry, and timing all at once. Radiation pressure sat there, cool and indifferent, asking only for an extreme area-to-mass ratio. That's the moment everything tightened. If it's outgassing, where's the gas and dust? If it's sunlight, what kind of body can catch that much momentum and still survive the trip? Those ghosts weren't going away. They were leading us back to the orbit fit, where the numbers would make the next call. The trajectory problem. Back at the orbit machines, the romance dropped and the math took over. You start with gravity-only fits, sun, planets, relativistic nudge, and watch the residuals, those tiny differences between where the object should be and where it is. For 3I Atlas, the residuals marched in a pattern. Nudge the parameters, rerun, they came back. Add the standard cometary non-gravitational model, the Marston A1, A2, A3 terms that mimic outgassing thrust tied to solar distance. And the fit relaxed, then demanded something specific. A small, steady push directed roughly sunward. That direction matters. Outgassing jets love to push away from the sun when the day side warms. They can tilt with spin and topography, but the net force often leans anti-solar. Our fit said sunward. Not perfectly radial every night, but aligned enough that you couldn't hand-wave it as random jets. The magnitude was the other problem. At those heliocentric distances, even optimistic volatile mixes struggled to produce a thrust that big without leaving signs we should have seen. Dust brightening, gas lines, a coma fattening as the heating rose. Radiation pressure was the obvious check. Sunlight hits, photons impart momentum, and any object with a high area-to-mass ratio gets shoved. We ran the numbers the same way we did for Oumuamua. To match the observed acceleration, you need a cross-section per kilogram that's orders of magnitude above typical rocks or solid ice. If Threeey were a thin sheet, a shard with deep porosity, or a lacework aggregate, maybe it could live in that regime. But then survivability rears its head. Can such a delicate structure survive interstellar tides, micrometeoroid hits, and thermal cycling near perihelion without crumbling? Spin coupling added another layer. The Yarkovsky and YORP affects matter over years, even decades, not weeks. We tried to stretch them anyway. They wouldn't. The thermal lag that can create day-night anisotropy didn't line up with the observed acceleration changes. When the brightness curve hinted at certain orientations, the force didn't neatly follow. Parameter sweeps became the daily grind. Change the sublimation law, water ice, Co2, tie it to heliocentric distance with different exponents. Let the effective active area evolve. Now spin it, add a processing pole, tilt it, make the jets migrate. Every knob got a twist. You can make outgassing match the magnitude if you allow a large active area and low dust yield, but then the coma limits kick you in the shins. You can hide gas if it's dominated by species we're blind to that night, but multiple teams shot at different lines across multiple nights. The absence stacked up. We brought in error bars with a vengeance. Astrometry has systematics, catalog offsets, color terms, trailing losses. Photometry, 2 aperture choices, gradients, 0-point drift. Everyone scrubbed reductions. We tossed bad frames, downweighted marginal nights, re-referenced against Gaia, checked for biases. The acceleration signal held. Shrink the bars, shift the centers, it stayed. Meanwhile, the directionality persisted. Plot the acceleration vector against the sun object line, night by night, and it hugged the radial. If jets were doing it, they'd need to conspire with the rotation so the net thrust pointed sunward over many spins. That isn't impossible. Spin-locked active regions can bias thrust, but the required stability under chaotic tumbling looked like a magic trick. The light curve's instability hinted at changing orientations. The force didn't wander enough to match. Radiation pressure kept sliding back into the conversation because it doesn't need that choreography. Give the object a big reflective area and low mass, and photons do the rest. The fit improved when we replaced the Marston outgassing law with a simple 1/R2 force proportional to solar flux. That proportionality is the tell. Outgassing follows a steeper or shallower curve depending on volatile. Radiation pressure tracks the inverse square law of sunlight almost exactly. Our best nights preferred the latter, not by a knockout but on points. Then we sanity checked with analogs. If Threeey were a fractal aggregate, think cosmic aerogel, its bulk density could plummet while its cross-section stays high. That helps the area-to-mass ratio without invoking a wafer-thin sheet. But the thermal model snarls. Open structures heat fast and cool fast. They're fragile under differential expansion. We ran a thermal stress estimate and didn't like what we saw near perihelion. You can make it work with small sizes and rapid cooling, but then the light curve amplitudes look odd again, unless you keep the geometry truly extreme. We circled back to the missing coma like it was a locked door. Deep stacks put upper limits on dust production that, when folded into sublimation recoil models, drop the available thrust below the required value unless the dust-to-gas ratio is weirdly low. Gas searches tightened caps on CO and CO2. You can still hide exotic ices. You can still invoke ultrafine, radiation-dark grains that evade detection, but each escape hatch narrowed. By the end of that week, the room split into two clear camps, not by belief, but by prior. One group said, stay with outgassing, push the composition and geometry until it breaks. The other said, fit the force that the data wants, radiation pressure is cleaner. Both agreed on the headline. Gravity alone wasn't enough. The trajectory needed a shove that nature can supply in a few ways, none of them comfortable under our constraints. The next observations would decide which discomfort we could live with. The missing Coma. While the orbit fit tightened around a sunward shove, the images kept refusing us the one thing that would make outgassing honest, a coma. Teams pushed their stacks deeper, layering hundreds of exposures, shifting them along the object's path to keep the signal sharp and smear the stars. Then they measured how faint a halo they would have caught if it were there. The thresholds were brutal. If a dust haze existed above those limits, we should have seen it. We didn't. So we translated non-detections into numbers that hurt. Upper limits on dust production became grams per second, then kilogram per second caps across grain sizes. Dust emission sat well below typical comets at similar distances. Fine, maybe gas-dominated with almost no dust. Then you hunt the gas. Co near 4.7 microns, Co 2 via indirect bands. Nights went by with nulls and maybes that wouldn't hold. Every null tightened the cap. Every cap squeezed the thrust budget. Meanwhile, the sublimation physics stared us down. At that heliocentric distance and phase angle, the expected heat budget tells you how much energy hits each square meter. You can only spend that energy two ways: re-radiate as heat or convert some of it to latent heat to lift molecules. If you claim a thrust from sublimation, you're claiming a certain mass flow. That mass flow should glow in lines, thicken a coma, or brighten the dust. With each upper limit, the ledger stopped balancing. The recoil thrust we needed wasn't buying any of the signatures we should have been able to afford. We tried to hide the gas in chemistry. Exotic ice mixes became the last refuge. Hydrogen. Interstellar UV would have chewed it long before arrival. Nitrogen. You'd need a crust and a history that were hard to square, plus nitrogen features love to betray themselves. Co looked best on paper, but the absence of its line across multiple tries got louder. Maybe it's a cocktail, Co with a pinch of something we weren't tuned to catch those nights. The problem is, a cocktail still needs a bottle. Where was the haze that bottle should leak? Dust itself could be tricky. If grains are ultrafine, they can be pushed away quickly, diluting the local density below our surface brightness limits. If they're large and dark, they can stay close but contribute little light. We ran both angles. The fine-grain model helps you hide brightness, but tends to create broader tails we'd catch in deeper stacks. The big-grain model hides in the glare but torpedoes the available thrust because those grains eat momentum. Every tweak felt like squeezing a balloon. Fix one part, another bulges. Then there's the surface physics. What if the object carried a refractory mantle, a crusted skin that chokes dust and vents gas through microcracks? That can lower dust-to-gas ratios and mute Coma. It also creates anisotropic jets, tiny vents acting like pinhole thrusters. Good for thrust direction maybe, but again, we ran into energy accounting. To get the measured acceleration, those pinholes need serious mass flow. The gas has to go somewhere. Even if it's invisible some nights, you don't get to erase it every night. A careful team revisited the stacks with a different tactic. They subtracted a synthetic point spread function tuned to the object's motion, then looked for residuals that fan out just beyond the seeing disk. If a coma was hiding right at the edge, this would snitch. The residuals were flat. An independent pipeline reproduced the flatness. We started to say the quiet part plainly. If outgassing is doing this, it's doing it with remarkably little evidence of itself. Radiation pressure doesn't need a coma. It only needs cross-section and sunlight. That's why the missing coma kept tilting the room. The more we tightened dust limits and gas caps, the more we forced natural models into narrow corridors with slippery floors. The Comet playbook wanted to help. The data kept slamming it shut. There was one last refuge: transient jets. Short, sharp bursts could produce thrust without building a steady coma if they were brief and rare. So we cross-matched photometric spikes with astrometric nights. If a burst shoved the object, the light curve might twitch. We found a couple of coincidences, nothing that survived a harsher cut. The acceleration term looked steady on multi-night scales. Transients didn't explain steady. By the time we closed that door, the conclusion wasn't a declaration. It was a posture. We'd given the coma every chance to show itself. It didn't, which meant the composition and surface physics would have to be strange, or the force was something that never needed gas in the first place. That's when geometry stopped being a curiosity and became a constraint. If sunlight's the pusher, what shape lets photons grab hold this hard without tearing the thing apart? Inside the ice, composition clues. We turn to the spectrum because when images go silent, chemistry can still talk. A shaky near-UV run hinted at a CN feature, weak, barely a shoulder above the noise. Another night in the near-IR nudged where CO could sit. Both came with caveats: calibration drift, airglow ripples, cirrus. Still, we logged them. You don't throw away whispers, you stack them and see if they harmonize. Then came the nickel debate. A late-session reduction showed a faint line near a nickel transition, trace metal in the tail end of a spectrum that barely cleared the floor. Some argued contamination, telluric leftovers, instrument scatter, an aggressive flat field that printed a ghost. Others said if it's real, nickel at that level would hint at refractory inclusions, metal-rich grains that survived where ices evaporate. We reran the pipeline with stricter sky subtraction. The line sagged but didn't vanish. Verdict: suggestive, not decisive. And that word, suggestive, drove everyone a little mad. Composition isn't just labels, it's leverage on force. If CO or CO2 really were present, even at low levels, they could power jets that don't throw much dust. But the energy budget wouldn't bend. At the observed flux, the mass flow implied by the non-grav push outpaced our line caps. Unless the surface was channeling gas through narrow vents that we caught at all the wrong times, the math didn't balance. We tried a different angle. Maybe the surface was darker than we thought, making the object larger, so you need less acceleration per kilogram. That helped for a day. Then the light curve amplitude yanked the rug. Extreme swings implied either a smaller, shinier object or an absurd geometry. Both pushed us back toward high area-to-mass territory. So we asked what could make a small body look bright without being massive. Porosity is the lever. If the interior is voids, think cosmic pumice. The mass plummets while cross-section holds. That pumps the area-to-mass ratio, making radiation pressure matter more. Density estimates for fluffy aggregates can drop to tens of kilograms per cubic meter. That's inflatable castle territory. But porosity alone doesn't tell you reflectivity. Space weathering steps in. Organics and tholins build dark mantles that swallow light. If Threeey carried a darkened crust with embedded bright patches, fresh ice windows, frost veneers lodged in pits, you'd get a low average reflectance punctuated by sharp glints. Those glints could explain the asymmetric peaks we kept chasing. We walked the weathering timeline. In interstellar space, cosmic rays bake surfaces, welding organics into tar-like skins. Micrometeoroid pings chip edges and roughen texture. Closer to a star, thermal shocks shed flakes and expose fresher layers. If Threeey had a crust that periodically peeled, it could flash bright then dull as facets turned. That dynamic fits the it moves phase angle slope steeper some nights, flatter on others, as surface states rotated in and out of view. It also hints at another trick: specular reflection. A smooth patch can act like a mirror. If that mirror is thin frost over a void, you get a large optical cross-section without much mass underneath. We kept circling back to the weak CN hint. CN often tags along with other volatiles. It can be a tracer for general outgassing. If it's barely there, either the activity is truly minimal or the source compositions are odd. Nitrogen poor, carbon lean, or bound in refractory organics that don't crack easily. We checked calibration stars, nudged extraction apertures, and compared against nights with different seeing. The hint persisted within wide bars. It was like the object was telling us, yes, I breathe, but not enough to move me the way you think. That led to the density game. If we could push the bulk density down, the same force produced a bigger acceleration. We mapped brightness to size under different albedos, then mapped size to mass under different densities, then asked what radiation pressure would do. For a dark, compact body, the shove was trivial. For a bright, porous one, it grew. The sweet spot, where the measured acceleration matched photon push, wanted either a thin sheet geometry or a fractal with a terrifyingly high porosity. Both live in the same neighborhood. Lots of area, not much mass. Space weathering gave us one more card. A dark mantle can hide fresh ice until thermal stress opens cracks. Those cracks vent briefly, frost nearby surfaces, and create bright, transient patches. If the object was tumbling, a frosted patch could swing into the sun, reflect hard, then sublimate away, leaving a dull scar. That cycle would rewrite the light curve night to night and confuse period fits. It would also create tiny, short-lived jets that are easy to miss spectroscopically, yet too feeble, on average, to account for the steady shove. In other words, the chemistry could be noisy while the acceleration stayed calm. Then a geometry twist snapped into place. If the body had concavities, deep pits, lattice-like voids, the same projected area could swing wildly as it turned, flipping our brightness to size assumptions. A lightweight snowflake shard laced with holes could look huge when faced on and skinny when edged, while weighing far less than a solid slab. That's composition masquerading as shape and vice versa. It also dovetailed with the nickel whisper. Metal-rich flecks embedded in a porous matrix would survive where ice retreats, seeding specular glints without adding much mass. Put plainly, the spectra gave us cautious hints of volatiles and maybe metals. The photometry begged for high area to mass. The weathering story explained the jitter. None of it proved radiation pressure, and none of it saved outgassing from the missing Coma trap. But together, they pushed us toward a constraint that wouldn't budge. Whatever Threeey Atlas is made of, it either hides its breath with remarkable efficiency or carries a structure so airy that sunlight can push it around like a leaf. Geometry games, sail, shard, or snowflake. Here's where geometry stops being poetry and becomes a calculator. Start with the thin sheet scenario. If Threeey Atlas is a wafer, a few hundred microns thick, meters to tens of meters across, the area-to-mass ratio skyrockets. Sunlight finally gets leverage. The radiation pressure term that fit our orbit wants that leverage, but survivability hits you in the face. A true sheet has to ride out micrometeoroid hits and thermal cycling. Every tiny impact can seed a tear that runs. Every degree of differential expansion can wrinkle, warp, or snap a brittle film. You can mitigate with high-toughness materials, but now you're speccing engineering, not geology. Could nature make a sheet? Ice veneers form, but they're fragile and usually bonded to substrate. Loose films don't last long in heat. So pivot to a fractal or porous aerogel comet. Think snowflake physics at cosmic scale. Sintered ice dust aggregates with voids everywhere, bulk density down in foam territory. The advantage is obvious: huge cross-section per kilogram without requiring a literal sail. The drawbacks pile up fast. Porosity means high surface area, which means rapid thermal response. The sun side heats quickly, the night side cools quickly, and the stresses concentrate along thin struts. Near perihelion that can trigger structural avalanches, whole lobes slumping, shards detaching. The upside: a catastrophic shed could explain sudden light curve changes and even seed those specular glints if fresh, smooth fracture planes are exposed. The downside: keep doing that and the object's personality should change more violently than we observed. Shard from tidal disruption sits in the middle. Picture a parent body grazing a star or getting yanked apart in a planetary pass eons ago. Flakes peel, mantle plates splinter. You're left with brittle sheets and ribbed fragments with deep concavities. A shard gives you extremes. In one orientation, it's a billboard. Rotate 90 degrees and it's a knife. That matches our amplitude without inventing impossible spins. It also answers the survival test better than a pure film. A fractured slab of sintered ices and embedded mineral grains can hold together long enough to cross a system, especially at modest sizes. The fractures create cavities and edges that drive specular flashes. The catch is the same one we keep tripping over. If it's ice-rich, warming should vent. If it's ice-poor, how do you explain any volatile hints at all? Tumbling complicates everything and helps. Complex rotation, not a single-axis spin, can scramble the phasing between light curve peaks and any force anisotropy from outgassing. It can also time-average radiation pressure effects. A flat-ish shard that tumbles still feels a net sunward push because photons keep coming from one side of the sky. Meanwhile, the glints and amplitude chaos make sense as facets and voids wander through sunlight. We tried chaotic rotation models with non-principal axis spin and found sweet spots where you get high amplitude, drifting apparent periods, and a fairly stable net force direction. Those are rare in parameter space, but they exist. Rare isn't impossible for a single object. Then there's the ghost in the room, the artificial sail baseline. It's not a claim, it's a measuring stick. Breakthrough starshot studies gave ballpark numbers for micron-thick, meter-scale sails made from graphene-class composites with reflective coatings. Those numbers live right where our area-to-mass ratio wants to be. Such a sail would be specular, would glint, and would feel radiation pressure exactly the way our fit prefers. It could survive near-sun passes if coatings manage heat, and if the sail spins for passive stabilization. But real sails accumulate scars, pits from dust, rips from hits, edge curl from thermal fatigue. A damaged sail starts to look like a shard. That's the unsettling overlap. An engineered artifact in failure can mimic a natural fragment, and a natural fragment with the right fractures can mimic a battered sail. We ran micrometeoroid risk against interstellar densities. Over millions of years, a thin sheet takes hits that perforate. Perforation lowers mass more than area, briefly improving the push until a crack connects the dots. A shard, by contrast, loses edges and sprouts bevels but tends to endure as a stubborn core. That leans us toward shard over pristine sail for longevity. Yet the photometric phase behavior, those sharp, asymmetric spikes, is friendlier to specular patches than uniformly rough rubble. A shard with smooth fracture planes and occasional frost veneers gives you both. Natural origin, sail-like glints. Thermal models press the case. A snowflake aggregate bakes fast. Its microstruts fail early near perihelion unless it's small. Small helps the survivability but stresses our brightness unless albedo is high. A thin sheet handles heat if it's reflective and rotates, but then any loss of spin stability raises temperatures dangerously. A fractured slab can self-shadow, reducing peak heat, while concavities trap transient frost. That explains brief brightening without a sustained coma and keeps structure intact. Tumblers also solve the direction puzzle. If outgassing were the driver, chaotic rotation should smear thrust direction unless active areas stay sun-locked, which they don't under non-principal axis motion. Radiation pressure ignores that chaos. It cares only about projected area. We saw a steady sunward push with noisy light, exactly the signature of photons working while the geometry throws a tantrum. So where do we land? Sail, shard, or snowflake? The clean sheet is elegant but fragile and drifts into artifact territory. The pure aerogel snowflake is efficient but thermally nervous near the sun. The shard, born of disruption, light enough to feel photons, faceted enough to glint and tough enough to last, threads the constraints we have. It doesn't prove radiation pressure. It makes it plausible without invoking an alien workshop. Next, balance the force and energy budgets against this geometry and see if the numbers hold. Energy accounting, the force budget. Time to open the ledger. Sunlight delivers a known paycheck, about 1,361 watts per square meter at 1 AU, falling as 1 over r squared. Convert that flux into momentum, and you get roughly 4.5 micronewtons per square meter of perfectly reflecting surface at Earth's distance. That number is the backbone. If radiation pressure is doing the shoving, the required projected area for Threeey Atlas is simply the observed acceleration times its mass divided by that micronewton per square meter budget, scaled by distance. Every shape, every material, every spin state has to live inside that arithmetic. We bracketed size from the light curve and albedo guesses, then mapped to mass under different densities. A compact, rocky shard with a few percent reflectivity forces the required area to absurd levels. The photons couldn't pay the bill. A bright, porous fragment drops mass steeply while keeping lots of cross-section. Suddenly, the numbers start to meet in the middle. At 1 AU, if the acceleration term is on the order of 10⁶ meters per second squared, you need tens to hundreds of square meters per kilogram for a comfortable match. That's thin sheet territory or extreme porosity. Push the distance out and the flux falls. The area to mass requirement rises accordingly. Our measured push didn't fade faster than 1/R2, which kept radiation pressure on the table. Now the sublimation ledger. Outgassing thrust is mass flow times exhaust speed divided by mass of the body. Covents around a few hundred meters per second. Water is slower at those distances. To hit the observed acceleration, you back out a mass flow that should light spectral lines or at least puff a coma above our limits. But the lines didn't stand up, and the coma caps were tight. We tried to squeeze more thrust by invoking collimated vents, pinholes that act like nozzles. Collimation multiplies momentum per molecule, but physics charges a fee. Narrower vents clog, heat locally, and need higher pressure. That pressure requires more energy. Energy we only had in the solar budget. The math kept circling back to the same shortfall. If you push the mass flow high enough to move the object, you should have paid for visible signatures. We didn't see the receipts. Thermal lag was the next loophole. A rotating body heats on the day side and keeps venting from warm subsurface layers as it swings into night. That can skew thrust directions and smear timing. We modeled day, night anisotropy with different thermal inertias, from cork-like to rock-like. The phasing didn't cooperate. Nights when the acceleration vector hugged the sunward line didn't align with the lags our best-fit spins would produce. Increase inertia and you soften diurnal swings, but demand even more energy to maintain venting after sunset. Lower inertia and jets flicker with the subsolar point, which should have imprinted a stronger periodicity. The force looked too steady for either extreme. We checked other suspects. Solar wind drag is orders of magnitude weaker than photon pressure here. Charged dust coupling needs charged states and plasma densities that don't match, and directionality won't stay neatly radial. Yarkovsky is a months to years drift for kilometer-class bodies. Our window was weeks, and the magnitude was too large. Error bars can lie if you let them, so we got ruthless. Astrometry, trailing losses on fast movers bias centroid, we corrected with synthetic trail fits. Star catalogs, we anchored against Gaia, applied color terms, and tested for field distortions by rotating apertures across the PSF. Photometry, zero-point drift is a thief. We calibrated against nightly standards and cross-checked with independent instruments. Systematics survived the purge, a few but small. The acceleration term's significance dipped, then recovered as we removed noisy nights. On our cleanest subset, the sunward shove remained. Here, S where energy meets geometry. If Threeey Atlas is a fractured slab with concavities, its effective cross-section breathes as it tumbles. Radiation pressure cares about the momentary face it shows. Time average the projected area over a chaotic rotation and you still get a steady net push, modulated around 1/R2 with distance. Sublimation recoil, by contrast, depends on active patches, shading, self-heating, and vents that migrate as frost patches die. That should write a more complicated time signature into the force. We looked for it. We found hints, small wiggles, not decisive. The bulk of the acceleration sat where photons would put it, proportional to the sunlight, pointed roughly at the sun. Then the heat ledger closes the loop. Take the incident solar power on the projected area, Subtract the irradiated infrared given a reasonable emissivity and temperature, and ask how much is left to drive mass loss. Not much, unless the surface is dark enough to soak heat, but dark lowers reflectivity, which undercuts radiation pressure. Trade-offs everywhere. The sweet spot, the one narrow lane that fits all ledgers, wants a surface that reflects well enough to feel photons, a structure light enough to move, and a chemistry quiet enough to hide its breath. That's a shard with bright facets or frost veneers, not a gassy snowball. We ended that night with a number on a whiteboard, required area-to-mass ratio with fat error bars. Under it, 2 columns. Left, photons can do it. Right, gas must be invisible and efficient. Both were possible. Only one didn't owe us missing energy. Inside the rooms, arguments, doubts, lines in the sand. By the time the force term wouldn't go away, the science moved from telescopes to rooms, Zoom windows, cramped seminar tables, hallway knots after colloquia. People didn't argue about aliens. They argued about error bars. A senior dynamicist opened with, "Extraordinary claims need extraordinary evidence," and everyone nodded. A younger postdoc said, "Follow the data where it leads," and the temperature ticked up. Drafts flew. One team circulated a preprint that leaned hard on radiation pressure with a cautious headline, "Constraints on Non-Gravitational Acceleration of Threeey Atlas." The abstract was pure restraint, the figures were not. A clean 1/R2 fit line sat there like a dare. Within hours, a rebuttal thread started in a private channel. "Your astrometry stacks bias centroids under trailing. We corrected with synthetic trails. Show the residuals without downweighting." Screenshots arrived, arrows on plots, captions typed in a hurry at 1 a.m. Meanwhile, proposals sat on desks. If you wrote Technosignature anywhere near an observing request, you risked scaring time allocation committees. If you didn't, you risked missing the only chance to catch a glint that would decide the argument. A program officer sent a careful note. "Frame this as a physical constraint study." Translation: don't spook the reviewers. In a different inbox, a journalist asked for comment on the alien sail in our backyard. Nobody replied. You don't want your name in that headline before the figures are bulletproof. Grants and reputations sneaked into the math. A mid-career PI who'd staked years on volatile-driven models looked at the Coma limits and said, "Push the chemistry before you jump to photons." Not dogma, experience. Across the call, a materials physicist with no dog in the comet fight said, "Your force law matches light, not gas." Both were right within their priors. That's what made it a fight worth having. The room wasn't split into believers and skeptics. It was split into what each person thought the universe prefers to do when you corner it. History kept walking in uninvited. Someone said Martian canals, and someone else said cold fusion. Both were cautionary tales, seductive patterns that evaporated under better instruments. Then a third voice said Oumuamua scars, and the chat went quiet. Everyone remembered the bruises, careers dinged by quotes out of context, papers rushed into print, years spent defending careful words from careless headlines. One astronomer who'd been dragged through that churn unmuted. Write what you can defend with hostile referees, nothing else. Reviewers became characters. Referee A, ruthless on systematics, allergic to speculation, willing to bless a radiation pressure parameter if you called it effective cross-section scaling. Referee B, generous on physical intuition, insisting you test an outgassing law you'd already broken 3 ways. Referee C, the ghost who asked the one question nobody wanted to face. If you're right, what observation tomorrow would prove you wrong? That line drew an actual line in the sand. A polarization signature, a specular glint cadence, a late-appearing coma. Teams started drafting tests before drafting conclusions. Inside a lab at noon, a small meeting found its edge. The lead said, "We can publish constraints without a headline and let the community infer the sail baseline." A postdoc shook her head. "If we don't name it, the press will, and we'll be playing defense." A grad student slid a printed figure across the table. Acceleration versus distance with 2 fits. Call it what the math calls it. Then add the sentence that keeps us honest. Artificial origin is not required, but we can't exclude it with present data. Everyone stared at the sentence, then at the door, as if a microphone might be taped under the handle. Preprints triggered preprints. One added a thermal fracture shard model that matched the light curve asymmetry without invoking films. Another reprocessed gasline searches and shaved the code cap a bit tighter. A third pointed out a calibration bug in a popular reduction script that, if uncorrected, would fake a tiny coma. The bug fix didn't change the conclusion. It did quiet a loud critic. That's how the sausage gets made, not in a eureka, but in a pile of small rescues. Then the risk calculus went personal. A junior researcher asked privately, "If my name is on a paper that mentions a probe, do I get a job?" The answer wasn't a speech, it was a pause. A senior said, "Say Lightsail-like regime and anchor it in numbers." The internal memo that set the tone had 6 words circled: describe, constrain, predict. Do not declare. Under it, a to-do list: polarization campaign, high-cadence glint search, deep late-time stacks. Decision time arrived on a Wednesday night. The draft's final paragraph was blank. Somebody typed, "We publish conservative constraints with a provocative final line." The line read, "A passively accelerated geometry, natural or engineered, fits the data best under current limits." It was the least explosive way to say the loud part. They hit send to the journal and braced for the reviews. While telescopes stared outward, those rooms held the actual heat. Doubts sharpened into tests, egos trimmed by error bars, and a community drawing boundaries it might have to cross. Only then did they allow themselves the next step. Step outside the building and ask, as a working thought experiment, what an engineered probe would have to look like to live inside these numbers. The probe hypothesis, a working thought experiment. Call it a thought experiment, not a claim. Start with propulsion. If you build a probe that doesn't burn fuel, you let the star push it. A Lightsail doesn't need exhaust, just photons. The measured acceleration lives in the same ballpark as a thin, reflective sheet with a high area-to-mass ratio. Starshot studies gave guardrails, micron-thick films, tens of meters across, graphene-class substrates with dielectric coatings to survive heat, spin for stiffness so wrinkles don't grow into failure. If Threeey Atlas sits in that regime, sunlight is your engine. Materials decide survival. A workable sail needs high reflectivity to stay cool and low aerial density to feel the push. Graphene laminates, aluminum or dielectric stacks may be a metamaterial pattern to tune thermal emissivity. These aren't sci-fi, they're on whiteboards in labs. Micrometeoroid hits are inevitable. You mitigate with redundancy, mesh-like lattice, microribs, ripstop architecture. Perforations bleed mass more than area, actually improving the push for a while. But tears run. Edges curl. A century in Interstellar, grit turns pristine films into ragged shards. That decay path is important because a damaged sail can masquerade as a fractured natural slab while still riding photons. Navigation without fuel forces cleverness. Spin stabilization keeps the plane flat to the push. Attitude control can come from tiny reflectivity gradients, patches that switch from mirror to absorber with simple shutters, or microflaps that trim the angle of attack by fractions of a degree. You don't need dramatic maneuvers. For a passive courier, it's enough to keep the broadside roughly sunward, averaging out tumble into a net push. Even failure can be a feature. If actuators die, the craft devolves into a free tumbling reflector that still tracks in 1/R2 acceleration law. That's exactly the signature our fit likes. Purpose shapes design. Why fling wafer probes between stars? One use is listening posts, passive sensors that drift through systems, sniffing magnetic fields, chemistry, radio noise. Another is data mules, storing forward nodes that hand off information via tight beam bursts when they pass a star with relay assets. Or breadcrumbs, a network sewn across the local bubble, each one a waypoint for future traffic, a map carved in photon sailing stones. None of those missions require a big bus or heavy instruments. A thin sheet with embedded chips, Edge-mounted coils and tiny power scavengers could be enough. The science fiction part isn't the function, it's the scale and patience. Now failure modes because the universe breaks things. A micrometeoroid holds the sail, tension redistributes, a crack runs and a corner peels. Suddenly you have a primary sheet and a cloud of splinters, each with high area to mass. The swarm flashes with specular glints and throws chaotic light curves while still summing to a steady sunward push. Thermal fatigue delaminates coatings, dulling reflectivity in patches. That lowers local acceleration, introduces asymmetries, and mimics the inconsistent period solutions we fought. In a worst-case spiral, the sail shreds into a shard, irregular, concave, glint-prone with concavities that boost amplitude. It looks natural. It flies like a sail. Engineered probes need power. Without fuel, you sip what you can. Solar when close, trickle charge from tiny PV strips along ribs, maybe thermoelectrics riding temperature swings. Deep space is lean, so you design for dormancy, wake near stars, sleep between. Comms. A wafer can carry a phased array etched into its skin, steering pencil-thin beams with no moving parts. If it's inert, no beacons, no chatter, we won't hear it. If it pastes a burst at perihelion, we'd need lucky timing and the right frequencies to catch a blink. We didn't. That doesn't falsify. It narrows what active could mean. What about mass and heat? Our energy accounting wants a surface that stays cool. High reflectivity helps. High emissivity in the infrared dumps heat. You can tune both with coatings. A reflective front, a radiative back, and a rotation that evens temperatures. Those choices keep a film alive inside mercury-like sunlight. If Threeey Atlas carried anything like that, the acceleration curve makes sense without a coma. Flip it, if the probe is actually a shard from a dead sail, the reflective bits that remain are the same ones responsible for the glints and the push. The rest, darkened, ragged, just rides along. Navigation intelligences leave fingerprints. A controlled sail would modulate attitude to maintain optimal push. That can imprint subtle deviations from a pure 1/2 law minute departures when the craft favors thermal safety over acceleration, or trims to dodge a hot spin state. Our data has room for small wiggles, but not for big choices. If there's a pilot, it's asleep or conservative. More likely, if this thought experiment is right, we're seeing a post-mission artifact coasting on physics, not an active vehicle making decisions. So what's the minimal engineered object that fits the numbers? A meter to tens of meters reflective film, aerial density around a gram per square meter or lower, carrying milligram-scale electronics, now punched, torn, and curled by time. It tumbles, flashes, and feels photons. Its mass is low enough that radiation pressure delivers the measured acceleration. It breathes no gas we can see. From a distance, it looks like a shard of something that once had a tidy plan. Before you ask the obvious, why here, why now, remember survey bias. Rubin and NEO Surveyor will see more of these travelers. If a network exists, we'll catch others and build statistics. Are there preferred sizes, brightness behaviors, orbits that cluster? A single detection is a story, a population is evidence. That's why this thought experiment matters. Not to declare, but to predict. If a Lightsail shard is plausible, there are signatures we can hunt. Polarization angles that swing like a mirror, glint cadences tied to non-principal axis spin, thermal deficits that betray thin-film heat capacity. Call it a working model, a passively accelerated geometry, engineered or natural, that makes sunlight the engine. If it's true, the sky will tell us the same story again. If it isn't, the next object will break this picture and push us back to chemistry. Either way, we gain a test we can run. Test, payoffs, and future traps. If you're going to let the data lead, you have to set traps the sky can't wriggle out of. The first trap was polarization. A rough, dusty coma scatters light in one pattern. A flat, reflective surface twists polarization with angle like a mirror. So teams planned a polarization sweep across phase angles, logging not just degree but the angle's rotation over a night. The payoff would be a telltale swing that tracked geometry, not gas. Miss it, and you give outgassing more oxygen. Catch it, and you hand radiation pressure a stronger case. Next came glints. Specular flashes don't behave like ordinary light curve peaks. They spike hard when a facet lines up with sun and earth, then vanish. We wrote glint hunting cadences with ruthless regularity, short exposures, high cadence, synchronized between hemispheres to follow the object through night and dawn. A true specular train should repeat at drifted intervals consistent with non-principal, laxus rotation, not a simple spinner. The payoff is pattern, not brightness. You don't need a blinding flash, you need a clock. Thermal deficits were the third snare. Thin films hold almost no heat. A shard that's all face and no depth should cool fast when a facet slips into night. That means mid-infrared flux that lags and fades sharper than a solid block would. If we could catch it with a sensitive IR instrument, even once, we'd weigh the heat capacity without touching it. Hard ask, but not impossible if you stack carefully and coordinate with optical to tie the phase. Radar was the long shot. At these magnitudes and distances, you're begging physics for a break. Still, a narrow window near closest approach might allow a chirp, just enough to constrain size or detect an anomalously large radar cross-section for its optical brightness. If a thin, reflective structure returned a stronger echo than expected, that would be a quiet, devastating clue. The trap here is practical. Transmitters booked solid, target faint, ephemeris uncertainty you can't afford. We penciled it in and knew we'd probably miss. Occultations offered a different kind of leverage. If the path crossed a bright star, we could stage a mini-campaign. Amateurs and pros along a strip, GPS-timed cameras pointed up. A thin object makes a thin shadow. A ragged shard makes a serrated light curve as edges and voids sweep the star. Even a single clean chord constrains cross-section brutally. The trap is cadence and luck, clouds, timing, and a target small enough to knife between stations. Still, we built the prediction maps and primed the network. All of that demanded a new kind of pipeline. We started building an anomaly layer, AI that learned normal for small body photometry and flagged deviations. Sudden polarization flips, glint-like spikes, phase angle slopes that moved too fast. Not to replace humans, but to wake them up at 2 a.m. with something worth losing sleep over. The payoff is reaction time. A glint that repeats needs eyes on it immediately, not 3 days later after someone finishes reductions. Surveys were the backbone. Rubin's LSSD would sweep the sky with cadence and depth that make one-off flukes into populations. NEO surveyor with infrared eyes could weigh heat when optics confuse. We drafted fast-react protocols. When an interstellar inbound flags, auto-cue polarimeters, high-cadence imagers, and IR instruments within hours. No more losing the first week to emails and committee lag. Build a standing playbook, then run it without asking permission every time. Hardware dreams crept in. A flyby microprobe is sexy in slides and brutal in budgets, but a CubeSat-class interceptor with a solid-state camera and a polarimeter isn't fantasy. Pre-stage a few in heliocentric drift and pounce when a track firms up. Sample return is for another decade. Flyby first. Get geometry, get polarization, maybe scrape a dust tail if it exists. The payoff is a single frame that shows an edge too sharp for rubble or a sheen too mirror-like for crust. We also plan for failure because every trap has holes. Polarization can be mudded by mixed textures. Glints need luck. Thermal deficits drown in background. Radar misses, occultations cloud out. The defense against bad luck is redundancy and speed. Many tests run early with overlapping coverage so a null in one channel doesn't end the story. And an honest rule, pre-register predictions. If you claim specular patterns, say when and how they should appear before you look. If you claim a shard's heat capacity, commit to a cooling rate. The payoff isn't just a detection, it's a prediction that survives. Meanwhile, data archiving got teeth. We wrote into proposals that raw frames, calibration files, and reduction code would hit public repositories on set schedules. That wasn't charity, it was armor. When the press spins, when the room gets loud, the best rebuttal is a plot someone else can reproduce at 3 a.m. with your pipeline. We built referee packs, scripts that take raw to figure and output the exact numbers in the paper. Hostile replication as a feature, not a fear. There's a future trap we didn't want to admit: confirmation bias. If the next object looks a little like Threeey, we'll want it to rhyme too neatly. So we wrote a contrary clause into the playbook. One person on each team is assigned to break the favorite model, design tests that would specifically embarrass it. Give that person veto power over headlines. It slows you down. It also keeps you honest when the clicks start calling. And if the verdict leans natural, great. We gain a new debris class and a story about violent planetary histories. If it leans engineered, then we're not just doing comet science anymore. We're doing neighborhood archaeology. Either path only works if the tests are on the calendar before the mystery shows up. The sky doesn't wait for us to finish our meetings. Meaning, if it's natural versus if it's not. If it's natural, we've just tripped over a missing branch in the family tree of debris, lightweight shards that form when worlds get violent. Picture a super-Earth with an icy mantle skimming too close to its star. Tides pull plates apart, fracture layers, and fling slivers into interstellar space. Over millions of years, the weak ones grind to dust. The survivors are the stubborn shapes: ribbed slabs, concave snowflakes, porous aerogel-like clumps. Every arrival like Threeey would be a postcard from someone else's disaster, the kind of planetary history you don't get from exoplanet transit curves. The stakes are big. A new class means new physics for small bodies, new pathways for how material moves between stars, and a revised idea of what interstellar space is sprinkled with. Natural also means we have to rewrite parts of comet lore. Our playbook assumes venting equals fuzz. Threeey says geometry and chemistry can hide their breath. That forces better models of crusts that choke dust, vents that act like pinholes, and aggregates that carry ridiculous area without much mass. If this class is real, Rubin will find more, and the scatter in their light curves will stop looking like chaos and start looking like taxonomy. You get subtypes: fracture slab reflectors, porous glitters, dark mantles with frost scars, each with predictable polarization and acceleration signatures. The payoff is practical. We learn how to sort them fast and decide when to spend precious telescope hours. But if it's not natural, if the shard lines up better with a sail that died on the way, then we're standing inside someone else's network. Not a grand, glowing fleet. Quiet hardware. Wafer probes seated along long arcs, using stars as engines, coasting for centuries. In that frame, Threeey Atlas is either a survivor or a fossil, a piece of infrastructure drifting through our neighborhood because infrastructure accumulates where orbits cross. That doesn't make first contact. It does change the question we ask when we see a thin reflector moving like a leaf. Is this geology or design? Artificial shifts how we think about technosignatures. We've been listening for beacons and searching for big heat. A passive sail doesn't shout, it whispers in dynamics and glare. The signature isn't a message, it's a force law. That turns the field from "are they broadcasting" into "are they leaving hardware?" You'd start writing proposals with words like non-thermal accelerant, specular cadence, and thin-film heat capacity. SETI becomes survey strategy, not just signal watching. Culture won't move on a straight line. If you say probe out loud, there's a reflex to flinch, to protect the science from the story. But stories shape what people look for. When Oumuamua lit the debate, the public leaned in while the field closed ranks. This time, the right version of the story might help. Not aliens visited, but we're testing whether sunlight can push a shard that looks engineered. That phrasing lets the audience hold the mystery without demanding a flag planted on either hill. The risk is obvious: headlines that outrun the figures. The counter is discipline: predict, publish, pre-register, and let the tape show whether you guessed right. Policy will lag and then sprint. If a future object fits the engineered template, strong polarization flips, repeating glints, a razor occultation. Who calls whom? There's no standing protocol for inert artifacts. Agencies have playbooks for hazards and radio detections, not for silent hardware on ballistic arcs. Messaging matters. Wait for replication before informing the public, coordinate international observations, and prevent a private actor from grabbing the narrative with a breathless press conference and a blurry plot. Personal stakes lurk under the math. Careers will bend toward whatever the data starts rewarding. If the next 5 objects look like Threeey, the young people who learn to chase polarization at 2 a.m. will own the niche. If the verdict comes back natural, the same skills still pay. They'll be the first to name the new class. The trap is reputation gravity. Once you publish a sale-friendly paper, referees will watch you for overreach. That's survivable if your code and predictions live in public, and if you hand your worst critic the mic occasionally. The people who play it straight will outlast the cycle. There's a quieter meaning tucked under both outcomes. Whether shard or sail, the phenomenon teaches humility about our default forces. Gravity is simple. Everything else cheats, gas hides, photons push, geometry lies. Oumuamua taught that with a sprint. Threeey is teaching it with a lab report. The better we get at catching these travelers in their first nights, the rarer the false choices become. Natural or not won't be a vibe, it'll be a checklist. And if you're asking which way this story bends, remember what the ledger said. Photons can pay the bill without owing missing energy. That doesn't crown an artifact. It tells us where to aim the next trap. Catch a polarization swing that tracks a mirror, pull a razor-thin occultation, or watch a late coma finally bloom and admit the chemistry just took its time. Either path carries meaning bigger than the label. One says planets elsewhere break in ways we can read across light years. The other says the void isn't empty, it's organized. Both say the same thing about us. We're finally building the patience to tell the difference. The crisis beat, one last data spike. 3 weeks after the first preprint, a late observation slid into the queue. A marginal night, thin clouds, mediocre seeing. Nobody expected much. Then the astrometry pipeline pinged red. The residuals kinked small, but enough to make a tired analyst sit up and run it again. Same kink. A small change in the acceleration profile, still sunward on average, but the magnitude dipped, then recovered with distance a hair faster than 1/R2 would predict. At 3 a.m., a microwave beeped and a mug overflowed. An email jumped to the top of the thread. Recheck force law exponent with last 4 nights only. Within minutes, plots multiplied. When we fit a strict 1/R2 law to radiation pressure, the new point sat low. When we allowed a slightly steeper exponent, 1/R2, 1/R2, 2, the curve hugged the data. Too small to crow about, too coherent to ignore. If that held, it would nibble at the clean sail story and hand a sliver back to sublimation, which often runs steeper. But there was a catch. The photometry for those nights showed no companion signature, no brightening, no broadened halo in the residuals, no spectral line rising above noise. The gas ledger still refused to open. So what moved? A geometry change can do it. If a fractured shard sheds a plate or flips into a less favorable attitude, its projected area shrinks, the push dips, then climbs as the tumble settles. That's a mechanical story, not a chemical one. We laid the two fits side by side. Steeper force law versus time variable projected area under a constant 1/R2 regime. Both could reproduce the wiggle. Only one demanded new physics on the force side. The room started leaning toward geometry. Meanwhile, a small team ran a polarization check on the same nights. The angle rotated a few degrees faster than before, consistent with a subtle change in facet dominance. Not decisive, not loud, but it rhymed with the geometry hypothesis. We stacked the evidence. Tiny deviation in the force curve, no gas signatures, small polarization drift, and a light curve whose asymmetric spikes shifted phase. 4 weak cards make a hand when they point the same way. By sunrise, the draft changed tone. The language hardened around what we could defend. We detect a small, statistically significant deviation from a constant geometry 1/R2 acceleration over the final week. The next sentence mattered more. This deviation is more naturally explained by a time-variable projected area under radiation pressure than by sublimation-driven thrust, given persistent non-detections of gas and dust. In the margin, someone typed, "Say the quiet part." Another replied, "Say the testable part." Then came the choice that would color the story for months. Do we publish a conservative conclusion and bury the big implication in the middle, or do we keep one provocative line in the abstract where nobody can miss it? The postdoc who'd fought for clear phrasing earlier put a finger on the table. Put it where referees will force us to prove it. The lead side nodded and moved the sentence up. A passively accelerated geometry, natural or engineered, remains the simplest explanation under current constraints. One more micro-story before we hit send. A grad student, eyes red, noticed a glitch in the centroiding script that me's-weighted elongated trails. If unpatched, it could have faked a tiny coma on one key night. She fixed it, reran, and the non-existent coma evaporated. That edit saved a paragraph and kept the arc clean. No gas, no dust, a wobble better told by shape. We closed with an open loop on purpose. The real reason for the final week deviation may not be clear for years, the draft now read. A late shed, a rotation state transition, or an unmodeled surface process could all produce the observed pattern. It wasn't a dodge, it was a map for future hunts. Predict the glint cadence after a shed. Predict the polarization swing of a rotation flip. Predict the thermal echo of a surface change. Then let the next object tell us which prediction lives. And with that, the email went out to the journal. The rooms got quiet. Outside, dawn burned the clouds a pale orange. We'd tightened the numbers until they squeaked, then left one door ajar. Not for hype, for the question we weren't done asking. The line we cross when we ask, what if? Asking the alien question doesn't summon spaceships. It forces sharper tests, honest priors, and answers without spin. If you want the follow-up when new data drops, subscribe so you don't miss the next trap we set. Then watch our Oumuamua deep dive to see how this puzzle started and what it still refuses to tell us.